today we will finish. We will prove that for any algebraic extension of K, if we have a complete ultrametric field, that any algebraic extension of K, the absolute value extend to for any algebraic extension of K. For that, we need first to prove that if we consider a finite extension of K, then the absolute value extends uniquely to L. The theorem then what we need to do is, if we consider, we need to define that what we will do, that assume that such an absolute value exists, and we will show that it is unique and is uniquely can determine such an absolute value uniquely. That's why assume that is on L, such that then when we restrict this absolute value to K, and we obtain our absolute value. Then this means when we consider when we have a field and we have an extension of a field, and our if this absolute value extend the one of K, then L with this absolute value is and since it's a finite extension, This means that L as K vector space is space. Dimension of L is exactly equal to N. And this means that L induced with this absolute value is a Banach algebra, K Banach algebra. What we want to do now is if we consider the K Banach algebra of just need to observe let alpha be an element of L and consider the map, the collinear map is a bounded map because we are in everything is finite and everything is okay. For any element X, we consider the multiplication by alpha. Then with respect to the operator norm of this operator is exactly equal and since we have this means that we compose and time this. This is exactly equal to alpha L, and it is exactly because it is a multiplication. Because it is an absolute value, then it is exactly equal to this. Then we have then this means that is equal to the spectral norm of this operator. Which means, and this means that the absolute value should be equal to the spectral norm of this operator. as I said yesterday, if we endow L with any equivalent norm, then the operator norm will be equivalent, and they have the same they have the same spectral semi-norm. That's why if and since L is a finite dimensional K-vector space, then each norm in this this space is all the norm are equivalent. Then it suffices just to define, for example, a norm on L, and we can define extend our absolute value to be the absolute value of alpha. If alpha is an element of L, just the spectral norm of this operator, the operator phi. And this means we should define because this one because since on L are equivalent, then is independent don't depend on the choice on L. Because if you have two equivalent norm on L, then the operator norm associated to this norm will be equivalent. And since we have, if two norms are equivalent, then their spectral norm are equal. That's why it is well defined, such thing. And since if phi beta is equal to phi alpha beta, which is equal to phi beta alpha, this means that then they for all alpha and beta in L then we have this is, as I said yesterday, when we are talking about the spectral phenomenon, if the two elements commute, then we can, if two elements commute, then we have the then we have the triangular inequality, and it is submultiplicative. Then, and we have this. And it is obvious that if alpha is in K, then the multiplication by alpha as an element of K can be seen as a diagonal matrix. And any norm, for example, if we consider the max norm, then we will got that the operator norm is exactly equal to the absolute value. And for this element, it will be power multiplicative. Then that's why we should have that the spectral norm of alpha will be equal to. Because this. Now, in order to prove that it is an absolute value, we just need to prove that it is multiplicative. For that, since we have the submultiplicativity, it remains just to prove just prove that and be careful. Yesterday when I introduced the operator norm, here I say specifically that n here n is a positive integer, because even if the spectral norm is power multiplicative, this does not mean that for example the spectral norm of the inverse is equal to the inverse of the spectral norm. That's why we need it's the point that we need to verify. And why this is enough? Because if we have if indeed and this one is equal to this one, then we will obtain the other inequality. And to prove this equality, I will give the following statement. If we prove that T alpha T cancelled. Is a minimal polynomial. Alpha, then in that case And the inverse, the minimal polynomial of just you can verify that it is exactly this one. This one. Then we will prove that the spectral norm of just is exactly equal to and if we prove that, we will observe directly that by doing that, we'll go directly that this one is exactly is -1. This coefficient. Now, how will we prove the section? It's not obvious. And then I need the following lemma. That reducible. Let's then we undo KT with Argos norm, the one that we defined yesterday. This one with center 0, of course. Here it's the center is C. Then let this just mean that if we consider the quotient of induced with the residue norm, then is exactly equal to the Gauss norm of the rest of the Euclidean division. This is what. Now we consider we set R equal to exactly A0 right? And then we know that for any alpha, k alpha is isomorphic to this. Which is a finite, finite k vector space. Everything is okay, and we know that each norm in this space are equivalent. Then everything. Then we have that. Then we can see L as a direct sum isomorphic. L in that case X. And if X is equal to something like X1, or the sum confused, and the norm of X is exactly equal to the maximum. In this situation, then multiplying by alpha can be seen also as then alpha restricted to k alpha is an element of and we have with respect to this norm, we can, by using this norm, we can prove that the spectral norm of semi-norm is the same if we consider this app as a collinear map over this K vector space. And here, with respect to this map, phi alpha here is exactly equal to operator norm equal to maximum of phi alpha restricted to K alpha, which means that exactly they are the same. That's why the spectral norm and as we said, then all we need to do is we know that the elements of K alpha can be seen if X is an element of K alpha, and we can write then X is equal to something like F0, F1 alpha, Fn minus. And with respect to the norm that we defined before, and the lemma that we state, is exactly equal to the maximum of Fi and if we multiply any element by alpha, then since it is a residual norm, and since alpha x is a representative of this element, that we know that this one is exactly equal to the nth of the Gauss norm alpha x plus p t qt for some qt in then we will probably have, since this one is a representative of this, then probably we will got alpha x r, which is exactly alpha x and since x has a degree less than m, sorry, here it's m, Then we have this means that the norm is less than alpha r, which is exactly in this case equal to this, because it is a Gauss norm and the alpha correspond to T by this isomorphism. And we have this. The other inequality is easy. Then this mean in particular that the spectral norm since we proved that they are equal, I don't need to write it each time. We know that here they are exactly, we know that they are exactly the same. Then I will just put this. Then the spectral norm is exactly less than now. The other inequality is easy to see. We know that since A0 is the product, I didn't say it before, but we can assume that here it's preferable to assume that L is normal, which means that if for any irreducible polynomial, if it admits a root, then it decomposes to simple elements. No, it decomposes in terms of degree 1. We assume that L and since by a root represented by the same matrix, as alpha. Then we have the and it is equal. Then this means is less is equal to then some alpha 1 alpha m minus 1, and they are, since they are all equal, then we have then we obtain the equality. We proved that since we got this, then we got this part, and since this one imply this one, then we obtain the we obtain that the norm is multiplicative. Yes, the spectral norm is multiplicative on L. Hence, it's defined uniquely. Define uniquely the absolute value, because it should be equal to the spectral norm of operator spectral norm. Then just as a remark, then we observe here that the key point of this theorem is that we use to prove that it extends uniquely is the fact that we are working with the finite dimensional K vector space, and since K is complete, then all the norms are equivalent on L, and that's why we can define can extend the absolute value in a unique way. However, for example, if we consider, then this can be extended to any algebraic extension, because we just need, if we have an algebraic extension, we define the absolute value for each element, and since each element can be in a finite extension, then we can extend the absolute value until the algebraic closure of the field. However, if we consider, for example, a field which is not an algebraic extension, and not really not, for example, I will just say it after, because after we just when we got an algebraic extension, probably it will not, generally is not complete. And if we complete, then it's still algebraic closed. and the absolute value will extend uniquely because it is the completion. However, if we consider a field, an extension of the algebraic closure, which is not algebraic, then the absolute value will extend not in a unique way. And for example, if we consider and this is the particularity of ultrametric fields. Yes, for example, this field. Therefore, for any value r, we can define then this field extends. If we suppose that K is algebraically closed, then this field is an extension of K, which is not algebraic, and we can extend the absolute value in many ways. And if for each value R, and not each element for this, we will see after, it will depend on the disk centered at A and with radius R. But for each R difference, we got a different absolute value, and they are not isomorphic. There is another point that I need to specify here. We observe here that if we have an irreducible polynomial, then when we extend the absolute value, then if the image by Galois group of an element alpha, then it will probably have the same absolute value. We observe that, for example, in the case of the Archimedean case, be careful, it's not true for Q. For example, if we consider a finite extension of Q, why it's not working? Because Q is not complete. However, it's well working on R because the field the proof is different is similar to this one, because it is R is a complete field, and each vector space with finite dimension is Banach, and all the norm are equivalent. Then this implies that if I consider an extension of R, then the absolute value will extend uniquely, and we know this absolute value is the norm on C, and we know that the conjugate of Z is exactly, the norm of the conjugate is exactly equal to Z. And there is something about Archimedean fields. Then, for example, for the big difference between ultrametric fields and Archimedean fields, then we cannot find a fields, an extension of fields of C, a complete extension of fields of C. We cannot. However, it's the case on ultrametric fields. And in somehow, that's why we have many problems in such situation. And as the corollary, This is a corollary from the proof. Then the map is an isometry, which means that it is a continuous map. It's a bounded map between the fields. Now let's talk about the most important lemma that exists in when we are working with ultrametric fields. The one that I told you before. When we are working with ultrametric field, then we have the residual fields, which sometimes is too smaller compared to the big one, and sometimes it can be finite with positive characteristic. And if we can found, for example, the following theorem say in some condition, if we can decompose our polynomial, when we reduce our polynomial to the residual fields, then if it decomposes in this field, then we can lift the decomposition to the big fields. And in particular, if there exists a simple root in the residual fields, then we can lift this root, and we call this the Hansel lemma. Just we need some notation to state everything well. Then we will. However, the important assumption that it should be a complete ultrametric field, because to construct the lifting, we will construct something like we construct the lifting by using sequences, and this we will prove that this sequences is a Cauchy sequence, which means that it converges and it exists. However, I will not give the proof, but I can give a reference where we can find the proof of this theorem. And when we say Gauss norm, it just means that R is equal to 1 and the center is equal to 0. Then we need to define what we mean by the reduction. And before that, if then a polynomial has coefficient has coefficients, which mean that the coefficients are bounded by 1. This is equivalent to say that the Gauss norm is exactly equal to and there exists that we call a reduction O from OKT to the residual field. In some sense, we can see we can see this one as the quotient of the closed ball centered at 0 with radius 1 by the quotient of the open ball open disk with center 0 and radius equal to 1. Anyway, and just reduce the coefficient here. And just be careful, if the Gauss norm is exactly less than 1, this just means that all the coefficient has an absolute value less than 1, and which means that their image in the residual field is equal to 0. Then Hansel lemma say and this just means that the reduction is not equal to 0. If O of P is equal to GT HT And the point that we need to be careful of it is the GCD of the two should be equal to 1. Because, for example, if I will just give you an example and come back to just here to if we consider, for example, we are in QP, and if we consider the polynomial equal to xp minus 1 in QP, then we can prove that this polynomial is irreducible. Sorry, not this one. This one. The cyclotomic polynomial on P. However, if we consider the reduction of such fields, then it is in FP. And we know that in characteristic P, this one is exactly equal to this one. And hence, it's actually equal to P minus 1. Then we have something it decomposed, but we can decompose, but the GCD between each one is not equal to 1. This means we cannot lift this decomposition. Then come back to here. That's why this assumption is important. Here, be careful. We can, for example, have if P has degree n, it can happen that the degree of the reduction be less than the degree of P. But if we have a decomposition, then it should, one of them should be equal to this. What I mean, one of them, for example, here it is G, should have the same as here. And if P has the same degree as its reduction, that probably H will have the same degree as its reduction. For example, if we consider in QP, just say always in QP, for example, we have something like that. Not just to be, I think, be simple. 3, something like. Then in this case, we will got something like that. And the reduction of P is exactly T plus T squared plus T. And in that situation, for example, we have T, and in this situation, we can lift this decomposition. And one of them should have the same, one of the lifting should have the same degree as its reduction. Then as a corollary, this is important. Simple rule just mean that it's just to satisfy this condition. Or just come back to the case of algebraic closure. Then theorem. To the proof of this theorem, you can use the Hansel lemma to prove it. And we know that the absolute value extends uniquely. And this is just the completion of the algebraic closure with respect to the norm. Then there is many proof for this theorem. I can give you just an idea, but it's not that clear. Too many ways to prove it. The idea is if we have a polynomial with coefficient in the completion, that each coefficient we can found a family of polynomial with coefficient in the algebraic closure. And in some sense, this polynomial will converge to the main polynomial idea. And if P is in then we can found a family of polynomial in the algebraic closure of T such that Pi converge to P in the sense of each coefficient converge this, let's say G, T, G. In the sense that HA G converge to AG. Then, if we have the coefficient converge to the coefficient of P, which we can construct because the algebraic closure is dense in the completion, then we have a theorem that I say if we have something like that, then probably the roots will converge to the root of this polynomial. And if Z E G roots and C G root of P, then we can prove something like the G converge to Z. It can happen that all the roots will converge to a multiple roots, for example. And since the roots converge to this means that they are Cauchy sequence, and this means that probably the roots will be in the algebraic closure. But it's not a rigorous proof. This is just to give you an idea about how we can do it. Then we observe that there exists, I think, for when we are using ultrametric fields. The first point is we need to complete. This is the first closure. Secondly, contrarily to R, for example, the algebraic closure is not finite. For example, for us, the algebraic closure has degree 2 with R. However, in the ultrametric case, generally, it is a non-finite extension of it's an infinite extension of K. This is a kind of problem. Then the algebraic closure is generally not complete. Then we need to consider another closure of this algebraic closure of K. And there exists another problems concerning such a fields. Then the algebraic closure is canonical. We can find it up to as isomorphism. The completion is also the same. This means that the completion of the algebraic closure is unique in some sense. But there exists another problem that we reach. If we are considering a complete ultrametric fields, then it can happen that if we have a sequence of closed pole, an infinite sequence of closed pole, no, sorry, nested closed pole, It can happen that their intersection can be the empty set, which is not. Which is not the case, for example, if you work with R or with C, this can never happen. And in some sense, we saw though when we use complete field, there is some gap where we have total discontinuity of the space. Then this means that there is many gap in our space, and it can happen that this one is like that there exists a disk who disappear from our fields. And for that, there exists something that and if this happened, then we can found another fields, an extension of fields, such that we will not have such a problem. And such an extension is called the spherical completion of our field, which is not canonically we cannot determine such a completion, spherical completion canonically. And this is interesting for some reason that we will see after in p-adic, because we will look to the solution around some point in another extension of our fields, not only in the neighborhood of the points of the fields. That's why. And the other point. And such there is some theorem. And for example, for the usual one in functional analysis is the open mapping theorem. This theorem holds when our field is complete and not trivially valued. This is okay, but there is another problem, Rham theorem, which cannot hold in a complete space. Then we need to be then the field need to be spherically complete to obtain such a theorem for ultrametric. Then we can stop here if you have any question. Then